This video will cover subtopic 6.2, the blood system. Here is a list of understandings, and there's quite a few of them, application and skills that will be covered in this video. So we'll start with a general overview of the circulatory system. So as discussed in the previous video, when the digestive system is going to bring nutrients into the body through absorption, those nutrients will have to move into the circulatory system. So those nutrients will then need to be transported around the body in order to get to the cells that require them. So this video will look at those various structures and organs involved in this transport system. So we'll start with the structure and types of blood vessels that are found in the body. So there are three types of blood vessels that are found. We have arteries, we have veins, and we have capillaries. So arteries will have three layers to them. There's a layer of, which would be endothelial cells, a layer of smooth muscle cells, and quite a thick layer, and connective tissue. Now some of the features of arteries is that they are able to stretch, so they have a high degree of elasticity to them. They are also very thick and very muscular. And arteries will also carry blood away from the heart. Often it's characterized that arteries only carry oxygenated blood, but this is not accurate. What is accurate to say is that arteries are classified as blood vessels that carry blood away from the heart, whether oxygenated or deoxygenated. Veins are also elastic, fairly elastic. They tend to have a thinner wall, and they will have a thinner wall to them, which is thinner than an artery. Veins will also have valves found in the lumen of the blood vessel. So these valves act as one-way flow, or allow blood to only flow in one direction. So if blood is flowing in this direction here, if blood tries to flow backwards, those valves will close and prevent backflow of that blood. And veins will carry blood towards the heart. Most of the times it will be deoxygenated. There's the one time where it is oxygenated, and we'll talk about where that happens. And then the third type of blood vessel are the capillaries. Now capillaries are very thin with a very narrow diameter. That diameter is one cell thick. So blood vessels or capillaries will be made up of a single layer of endothelial cells, not epithelial cells, a single layer of endothelial cells that will allow for the site of gas exchange with tissue cells and nutrient exchange as well. And capillaries are very abundant as well. This table goes through the various features that would allow you to identify blood vessels. So arteries are rather large, generally larger than 10 micrometers in size, whereas veins can be variable in size, but not much larger than 10 micrometers. And then capillaries are around 10 micrometers in size. Now arteries, as mentioned in the previous slide, have a relatively thick wall and will have a narrow lumen. The thick wall is due to the high pressure of the blood moving through the arteries, and so those walls need to be thick in order to be able to deal with that pressure exerted on them. Veins are relatively thin-walled, but often will be variable and will have a wide lumen. Now the thin wall in veins is due to the fact that veins are generally under low pressure and do not have to account for blood traveling with a high force. Capillaries, as mentioned in the previous slide, are extremely thin, less than or around 10 micrometers in size, and are essentially one cell thick. So we see here those capillaries will have only one layer to them, which is a single layer of endothelium cells, and those cells are going to be very thin. They're going to be very flat cells to allow stuff to move through them easily. Arteries and veins each have 3 layers to them. You don't need to know the names of those layers. And once again, veins are the only blood vessel that have valves. Capillaries and arteries do not have them. So kind of an overview of how the arteries and veins and capillaries are kind of found together. So as you have blood moving away from the heart in your arteries, they will enter smaller arteries, arterioles, that get smaller and smaller in diameter until they reach a point where they are only 1 cell thick. And these are the capillaries. So as shown in the diagram here, you have these endothelial cells that is 1 layer thick that surround those capillaries, and those endothelial cells are relatively flat as well. So in those capillaries, this is the site of gas exchange and nutrient exchange that will occur. So as O2 leaves those red blood cells in the capillaries, you'll have CO2 moving in. And as those red blood cells travel through those capillaries, they'll eventually enter into larger and larger veins and venules, which will ultimately lead into the vena cava, which will carry blood back towards the heart. So now, when you look at the comparison of size of these blood vessels and the pressure and speed at which blood is moving through them, if we have our arteries and our aorta is going to be the largest artery in the body, and this is the artery closest to the heart. As blood is moving through those blood vessels, and as that heart is pumping, these vessels will be under tremendous pressure, as shown in this diagram here, where there is high pressure, and this pressure wavers up and down because these blood vessels are basically picking up the rhythmic beating of the heart. But as that blood travels further and further away from the heart, blood pressure drops quickly. The pressure under which the blood is traveling drops quickly. Same with the speed. As that blood moves from arteries to arterioles, and then into capillaries, and then into venules, veins, and the vena cava, the pressure is very low, so that blood is not under high pressure at all. So moving that blood around the body is the heart. We'll start out generally describing the heart and move into kind of more specific features. So the heart has 3 layers to it. There is a smooth inside lining of the heart that is referred to as the endocardium. And then there is a middle layer of heart muscle that is referred to as the myocardium. And then that whole heart or that whole organ is going to be surrounded by a very thin fluid-filled sac called the pericardium. The fluid within the pericardium helps reduce the friction of the heart will experience while beating. This diagram just outlines the different blood vessels associated with the heart. So there is the aorta, which is the main artery coming off of the heart. This is the main artery that carries blood away from the heart. There is the superior vena cava, which is one of the main veins bringing blood back to the heart. There is also the inferior vena cava, which also brings blood back into the heart. And then, because obviously the heart is made up of cells, those cells need nutrients, the heart has its own blood supply. So those blood supply that is referred to as the coronary artery. So there is a right coronary artery, there's a left circumflex artery, and then there is a left anterior descending coronary artery. What you would need to know is that the blood supply to the heart is referred to as the coronary artery. Now, inside the heart is divided up into chambers, and separating those chambers are valves. So the heart is divided into 4 chambers. There is the right atrium here. There is the right ventricle just below the right atrium. There is the left atrium, and then just below that is the left ventricle. So each chamber has basically a one-way valve at its exit that will prevent blood from flowing backwards. So as blood moves through the heart, it should only move in one direction. So the valves that prevent this backflow are the tricuspid valve, which separates right atrium from right ventricle. There's the bicuspid valve, which separates left atrium from left ventricle. There is the pulmonary valve, which separates the right ventricle from the pulmonary artery, and the aortic valve, which separates the left ventricle from the aorta. So this diagram illustrates blood flow through the heart as blood is circulating throughout the body. So we'll look at the movement of blood first in the heart, and then consider its movement throughout the body. So blood entering the heart is going to come in through the superior vena cava. This is basically that main vein that is considered above the heart. And then there is the inferior vena cava, which will also lead into the right atrium. This is the vena cava that basically comes to the heart from below the body. From the right atrium, blood will get pumped into the right ventricle. From the right ventricle, blood gets pumped into the pulmonary arteries, where that blood is pumped off to the lungs to become oxygenated. So if this is our diagram here of of the right side of the heart, we have our right ventricle, or right atrium, sorry, and right ventricle. As that blood is leaving the right ventricle into the pulmonary arteries, it will enter into the lungs, and then you'll have gas exchange occurs where CO2 will be released, and O2 will be picked up by those red blood cells. Now, once O2 has been picked up by those red blood cells, that blood now travels back to the heart through the pulmonary veins. So the pulmonary vein will carry that oxygenated blood back into the heart, into the left atrium, and from the left atrium, that blood is pumped into the left ventricle. From the left ventricle, blood is pumped into the aorta and out of the heart. So here is the blood coming out of the aorta and traveling to the rest of the body. And then as that blood enters into systemic circulation, as it enters into various tissues, those vessels will start to get smaller and smaller until you have those capillaries where nutrient exchange will occur. And then blood that starts traveling back to the heart enters into those venules and veins, and ultimately the vena cava. So controlling all that movement of blood, obviously, is the heart that is contracting, and the heart will contract through a series of rhythms. So controlling the contractions of of the heart and those chambers are the specialized bundles of nerves found within the heart that will control the beating of the heart, and so it will allow that heart to beat in a rhythmic fashion, in a consistent fashion. The first bundle of specialized nerves is called the sinoatrial node, and this acts as the pacemaker and sets a rhythm of about 72 beats per minute. Now, the sinoatrial node is found somewhere at the top of the right atrium. There is a second specialized bundle of nerves called the arterioventricular node, or the AV node, and this will pass the nerve impulse to the ventricles which will cause them to contract. So the arterioventricular node again is found in the right atrium, but found kind of closer to the edge of the right atrium. So you'll have a nerve impulse, or an impulse that will start at the sinoatrial node and will spread to the arterioventricular node. The electrical impulse that starts at the sinoatrial node will cause the atrium to contract, and then as that electrical impulse reaches the arterioventricular node, it will travel to the ventricles, causing the ventricles to contract. And you get this rhythmic contraction of atrium and ventricles. So looking at how this electrical signal would spread and how it would cause the heart to contract, so you would get that electrical signal originating at the sinoatrial node that will start spreading throughout the atrium. This will cause a wave of contraction to begin and ultimately cause the atrium to contract. Now, as that electrical signal spreads, it will eventually reach the arterioventricular node. And here, the signal gets delayed for just a little bit to allow the atrium to contract. After a little bit of delay, that signal will then pass to the ventricles through specialized nerve fibers, and contraction of the ventricle will begin when that nerve impulse reaches the apex of the heart. And then this will start a wave of contraction that will contract the ventricle with force, pumping blood out of the heart. And then at this stage, contraction of the ventricles is complete, and the whole process starts over again. So the heart will start over again, where you'll get a wave of contraction that will cause the atrium to contract. That signal will then pass the arterioventricular node, which will then pass down into the ventricles, causing the ventricles to contract. So this ultimately forms what is referred to as the cardiac cycle. The cardiac cycle is the events related to the flow of blood that occur from the beginning of one heartbeat. So it's basically one heartbeat. The frequency of the cardiac cycle is also referred to as the heart rate. So there are two stages to the cardiac cycle. There is the systole and the diastole. The diastole begins with the contraction of the ventricles, and then at this point blood is forcefully expelled from the heart, where blood pressure is increased. The increased pressure causes the bicuspid and tricuspid valves to shut, causing the characteristic lub sound that you would hear if you were listening to a heartbeat. The next stage is the diastole. This is when the heart is relaxed and blood flows into all four chambers. The bicuspid and tricuspid valves are open at this point, allowing blood to flow into the left and right ventricles. During this phase of the cardiac cycle, pressure is reduced, causing the semilunar valves to close, creating a dub sound. So looking at this cycle of events that occur in the cardiac cycle in terms of that filling and contracting, so it all starts with the left ventricle here. So the muscles of the atrium wall will contract, pushing blood through the arterioventricular valves into the ventricles. Both atria will contract at the same time. This is referred to as atrial systole. So systole can be divided into ventricular systole and atrial systole. So the blood is then forced into the ventricles, causing the blood pressure inside them to rise, and then so you get the arterioventricular valves that snap close when the ventricles are full. The ventricle has to contract, generating pressure that drives blood through the semilunar valves into the aorta and the pulmonary artery. This is the ventricular systole, and then a pulse is produced that can be felt in the arteries and in other parts of the body. Now from here you have the ventricle contraction. So now you have the part where the heart is relaxed. All four chambers are relaxed, so ventricles and atria now relax, and the pressure inside them is low. The semilunar valves are closed by the back pressure of blood in the arteries. So the pressure here is basically keeping these valves closed. and this part of the cycle is referred to as the diastole. Blood then flows into the atria from the veins, opens the arterioventricular valves. Sorry about that. Blood from the body then enters the right atrium through the vena cava, and then blood from the lungs enters the left atrium from the pulmonary artery. The whole cycle is repeated again when the atria contraction begins again. So this whole cycle of arterial systole, ventricular systole, and then diastole repeats itself. And this is our cardiac cycle. So now, as that blood is being pumped by the heart and that blood is moving through the arteries, this creates a force on the walls of the blood vessels, especially on the walls of the arteries, and this is referred to as blood pressure. When blood pressure is measured, it measures the systolic and diastolic pressures of the blood filling and being expelled from the heart. So it's generally given as a ratio of systolic to diastolic pressure, and for the average adult, the pressure of that ratio is 120 millimeters of mercury to 80 millimeters of mercury. So heart rates can change, heart rates can speed up, they can slow down, and this is ultimately controlled in the medulla oblongata of the brain. So there is a cardiovascular center in the medulla oblongata within the brain, and it will receive input from receptors in the body which monitor blood pressure, will monitor pH levels, which will be related to CO2 concentrations as well as oxygen concentrations. So the pH of blood is reflected in CO2 concentrations, as when CO2 combines with water in the blood, it will form carbonic acid, lowering the pH. So if there's too much CO2 in the blood, that will lower the pH, making it more acidic. This is a signal that the brain will pick up, saying that there's too much CO2 in the blood, and heart rate would need to increase to try and get rid of some of this CO2. So the sinoatrial node will actually receive nerve impulses from the medulla oblongata to increase or decrease the frequency of heartbeats. So there's a series of nerves from the medulla oblongata in the brain that tell the sinoatrial node whether it needs to increase or decrease how quickly it is beating, or how quickly it is generating those heartbeats. Now, there are conditions which can restrict blood flow or blood movement through the heart, and this is generally referred to as arteriosclerosis. So arteriosclerosis is the development of fatty tissue called erythema, and basically you get this buildup of fatty tissue inside the blood vessel wall, which will narrow the opening in the vessel, or narrow the lumen, restricting that flow of blood movement through the vessel. So some of the causes of arteriosclerosis have been linked to things such as high concentrations of low-density lipoprotein, or LDL, chronic high blood glucose levels due to obesity and overeating. Chronic high blood pressure can be a cause of arteriosclerosis, and consumption of trans fats. Some of the consequences are that it will commonly affect the coronary arteries. Remember those arteries that supply the heart with the nutrients that it needs, which can lead to angina and myocardial infarction, or a heart attack. If you have a restriction of blood flow in the brain, this can affect the cerebrovascular circulation, leading to a stroke. In the arteries, it can lead to kidney disease, and in the aorta, it can lead to an aortic aneurysm, which is a rupturing of that blood vessel. So there are other factors that can control heartbeat and heart rate as well. A hormone called epinephrine is one of them. So epinephrine is a hormone that is produced by the adrenal glands and is also known as adrenaline. The adrenal glands are located just on top of the kidneys, and adrenaline gets produced in response to various stimuli. So the level of epinephrine will rise when physical activity is necessary to increase the heart rate. It is part of what is called the fight or flight response. As that adrenaline gets released, there are various physiological factors which happen in the body. So heart rate increases, your pupils dilate to take in more light, and you basically make a decision of, like, are you gonna stand your ground and fight, or are you gonna turn and run? So the flight response. So your body prepares for either one of those situations. In either one, you need a sudden burst of energy to perform either function. Lastly, IB wants you to know about a scientist by the name of William Harvey. William Harvey did work in various areas concerning biology. One of them concerned or dealt with blood circulation. So William Harvey overcame widespread opposition by publishing his theory and touring Europe. What he did was that he demonstrated that blood flow is unidirectional, meaning blood flows only in one direction, with valves present to prevent backflow. He was the first to suggest that blood returned to the heart through veins instead of being consumed by the body. The idea was that as blood flowed into the body, it got consumed by the tissue. And so it was very against the norm to suggest that blood actually got reused, that it actually returned to the heart. Now, he also predicted the presence of capillaries, although we could not see them. And he overturned a theory developed by a philosopher named Galen, which was held for thousands of years. So Galen was the one that suggested that as blood flowed out towards the body, it got consumed by the body and always was regenerated either in the heart or some part else in the body. So this theory had held for thousands of years, and through careful experimentation, William Harvey demonstrated that Galen was actually wrong, that blood actually was reused and was recirculated to the heart. So that is the end of this video for 6.2 blood systems.